Hi, my name is Prof. Joe. This is part of my lecture on measurement technology. Today talking about some more sensor technology, especially about strain gauges. So what is a strain gauge? What's the idea of such a thing? The idea is we have some wire. Imagine some ordinary wire we are stretching. What happens is that the wire gets thinner and longer. For that reason, its resistance will rise. Meaning, making a wire thinner rises the resistance, obviously, and making it longer also, obviously. And now, taking that idea and bringing it to some more extent, to some more usable way of deriving distances and length from that behavior is just to do something like meandering structures which are stretched and compressed in the way of the wire. And that is more or less, that's a strain gauge. Meaning we are stretching it, the resistance rises, we are compressing it, the resistance is going down. And that correlation, and that's the nice fact about strain gauges, is very simple. It's basically linear, meaning we have some definition of a correlation factor K, which is constant for short distances at least, which correlates the relative change in resistance to the relative change in the length of the strain gauge. This all together results in that behavior, which is typically for strain gauges, which says the relative change in the length of the strain gauge is directly proportional to a constant K, 1 over K in this case, times the relative change in resistance. So, what we are using those strain gauges for? The technological aspect is very simple. It's just, more or less, it's just a part of wire. We are stretching and compressing. And so we can attach it to anything we want to measure length changes. So attaching it to a bridge, we could measure the change in the bridge length of some parts of the bridge due to facts like summer, winter, and so on. We could attach it to any mechanical unit which vibrates or does something like that. But saying so, you for sure have realized it's not for measuring long distance changes. It's just for measuring small distance changes, especially changes in the range of micrometers, actually. One more application which is very common for strain gauges is the usage in weight applications, meaning units for measuring the weight, where strain gauges are placed within some, for example, metal casing, which then gets stretched or banded by an external weight. So placing a weight over there will stretch that thing downwards, will compress those two strains and lengthen those two on the top side, meaning placing strain gauges there, we get two strain gauges increasing the length and two strain gauges getting compressed, getting shorter, vice versa, meaning the change over here is plus delta L and the change over here would be minus delta L. And that can be used indeed for measuring weights and is used in industrial applications very much for measuring weights in any application you could imagine. For sure, as I said, you can place strain gauges wherever you want to. The simple way of applicating such a strain gauge is just gluing it somewhere. That's the typical way of doing so. So even the application of that strain gauge is very simple. And moreover, they are very stable. So they keep working and keep working, and they can be driven with high dynamics. A typical strain gauge would be able to deliver measurements up to the megahertz range of vibrations, for example, of a machine. For sure, those mechanical vibrations won't be that high, but for sure that means vibrations in the kilohertz range are no problem for a strain gauge. And for that reason, strain gauges are also very applicable to any vibration dynamical measurements. So overall, it's a robust, very flexible way of measuring short length scales. So, talking about those length scales, one thing has to be mentioned. Those strain gauges have a very linear behavior for very short distances. So meaning we are, for example, stretching that thing for 10 micrometers. And then suddenly at some stretching range, we get the problem of non-elastic deformation. So when that's the stretched length and that's the resistance, we get a very certain place where we more or less damage the strain gauge, meaning stretching the wire so long it persists in that elongated state. And being at that point, there's no way of returning, and the strain gauge more or less is destroyed, at least destroyed for its behavior it had before getting stretched too much. That indeed implies another fact about strain gauges. Strain gauges which are kept in an elongated state, which is applicable in the linear range, but are kept very long in that elongated state, will change their resistance over time. So, due to those non-elastic deformations when keeping something stretched, we get a resistance change over time when no dynamical changement of the strain gauge occurs. Having said so, the last thing to mention is how to measure those resistances, and the typical way is to use those resistance bridges we have already talked about, or I have talked about in some chapters beforehand. Whereas, if possible, 4 strain gauges are placed in a form like this, meaning 2 are elongating and 2 are compressing, and by that building up a full bridge which gives us a direct proportional voltage to the resistance change, and therefore to the elongation or to the shortening of the strain gauges. One could imagine a lot of other ways of electrical application, kind of just using 2 resistances depending on strain gauges and so on and so on. But the most typical way would be to use 4 strain gauges which change. Talking about those measurement bridges, temperature changes were always something which has to be respected when measuring resistances, because any material out there would or will change its resistance due to the temperature. Also, strain gauges will do so, but for sure we can compensate for that temperature change. The first possibility is to use those temperature compensations within the measurement bridges. Remembering the chapter on measurement bridges, we realize we can place the strain gauges in a certain way so the temperature influence of the resistance would be in the denominator and therefore very small. Moreover, strain gauges deliver us a second possibility to cope with temperature change. So imagine we have some measurement object over here and place some strain gauge on it. Temperature will induce several changes. The first change is due to the electrical resistance. talking about the iron bodies vibrating around due to the temperature. We will get some temperature change due to electrical effects. We will call the change due to the resistance itself, delta RR for this example at least, which can be described as a linear behavior, which is the base resistance time a constant beta correlating to the temperature change delta T. Moreover, we have other influences of the temperature. And the typical influence everybody knows is heating up some material will enlarge it. Same happens to the strain gauge. So we get an enlargement due to the temperature, which can be described as something like the strain gauge, I will call it M, to keep with the script, which is always correlated in the same way, kind of a constant K times another constant times the temperature change. Moreover, the same behavior will occur to the component, the measurement object itself. It will also enlarge with the temperature, but in a different way. So we get different constants, and let's call that the elongation due to B. RB, delta RB is R0. Again, always it's about that R0 times K times another constant times the temperature change. Taken all together, we get an overall temperature at the resistance change due to the temperature, which consists of three parts. Let's look at the relative change, which then is built up from three components, which are the change due to the electrical effects in the strain gauge itself, beta R times delta T, plus K times, and now the mechanical elongation due to the temperature, which goes vice versa, meaning those constants, those elongations drive in different directions considering the resistance. Why is that so? So the component we are measuring on elongates, and that means the strain gauge gets stretched. That means the resistance rises over here. Now, on the other hand, when the strain gauge gets warmer, it also elongates, but does not change its resistance due to the mechanical deformation, because it gets enlarged in every direction due to the temperature. That means that is in the different direction. The elongation, the enlargement of the strain gauge due to the temperature works in the other direction than that of the component itself. Moreover, that change due to the electrical effects, we can't do anything about that. But altogether, we could enforce that this change has to be zero by just defining that this has to be zero. We are able to define something like that because we can choose the materials sometimes. And for example, for that weight measurement application, for sure, meaning we choose a material over here, which compensates for the electrical change due to the temperature in the strain gauge. And we have some measurement weighting device, which would be temperature independent. And that's a usable, a good property of those strain gauges also, having some more possibilities to deal with temperature changes and temperature influences. Having said so, that's everything about strain gauges I wanted to tell you. The AI agent, link down below, provides you with some more detailed trainings and some more details about derivations of changes of resistances in strain gauges. But overall, strain gauges are a simple way of measuring short distances with very flexible dynamics, very stable measurement, and very robust technological applications, and additional good temperature coping mechanisms available. Having said so, have fun. See you next time.